We're going to expand on translation, and now you're actually going to be able to figure out, if I give you a sequence of DNA, what the mRNA looks like, and then what the protein looks like as a result. Remember that the central dogma starts with a DNA message that we read and we change to RNA, or specifically mRNA, but it has that little bit of a dialect difference. It's still nucleic acid talk, but it'd be like me talking in a British accent to you. You can still understand me, but there's a slight difference in what's going on. The mRNA is then translated into a completely new language out in the cytoplasm, the language of proteins, amino acids. It would be like going from English to British, and then from British to Spanish. Here we have the sequence of DNA, TAC, TAG, CGG, ATG, ACT. What is the mRNA going to look like? We're in RNA now, so there's no T's. Before, when we were doing this, we were making the other strand of DNA because DNA is double-stranded. Now we're looking at only one piece of DNA and a small section of it because this is our gene. Remember, a gene is only on one strand of DNA and it is small. So, what does the mRNA look like? Well, T goes with A goes with U, not T this time, and C goes with G. So our first is OG, and OG codes for a specific amino acid, which we will get to in the next step. Remember, OG is going to always be our start. TAG codes for AUC. AUC is going to code for an amino acid. What comes next? See if you can figure out the last three sequences, and then check with me once you get that done. Next, you should have GCC, codes for a different amino acid. Then after ATG, you have UAC, UGA. We haven't gotten it into the amino acid talk yet. This would just be like talking in a British accent. Same language, different dialect, using U's instead of T's. We have to go one step further to get it into a protein. How do we get it into this new language? Well, we have three kinds of RNA, and this one didn't animate. I guess there's one before it here. You need something to do the translation for you. In the case of translation in cells, our translator molecule is called tRNA, which we've seen so far. T, unfortunately, does not stand for translator or translation. T stands for transfer RNA because it's transferring in amino acids. What's really cool is that scientists know this code. We know the translation, and we know which each mRNA codon stands for. And we've put it together in a table and a wheel. They are the exact same thing, just some people prefer using one over the other. OG, if you use the wheel, you always start in the center. So you start with A, move to U, and the last letter is G. So OG codes for the amino acid MET, which we know, we've said that before, methionine. AUC, start with A, go to U, go to C, codes for ILE, isoleucine. Note, there's more than one way to get isoleucine. We could have AUU, AUC, or AUA. The code is redundant. Using the table, let's go to GCC. You always start on the left. So here's G. You find where your second letter is up at the top, GC. So I'm going to go here. GCC is right here. It's coding for alanine. Next we have UAC. Always start on the left if you're using the table. U, here's our second letter A. UAC is TYR. Lastly, UGA. UGA means stop, and that's when this process ends. We'll go through this again later, but I just wanted to give you kind of a brief overview of how it works. How we translate the DNA into protein. First, you have to use that codon or wheel to translate each set of three letters. Notice we're always working in three groups of letters here. Three groups on mRNA are called codons. Codons are code for amino acid. tRNA knows which amino acid to bring in because it has the complementary anticodon. So if on mRNA we have GCC, the tRNA that knows to come in is complementary to it. G pairs with C, C pairs with G, C pairs with G. Now let's go back to my table. GCC codes for, let's see, G, C, C, alanine, ALA. Sure enough, on the other end, this is alanine. Now it doesn't look like anything to you, but I swear this is alanine, the amino acid that is brought in when you have GCC. This is called on tRNA the anticodon, a set of 3 letters that matches the codon or is complementary to the codon on mRNA. Again, if you're using the wheel, you always start in the center and work your way out. If you're using the table, you start on the left, you go up to the top, and then you go to your 3rd letter and you find where it is. Redundancy, more than one way to get most of these amino acids. Please note that this right here is ILE, not LLE. So let's transcribe this gene. We have OG. Go back to your codon table or wheel, and you'll see that OG stands for MET. The tRNA matches up, the anticodon matches this codon, brings in MET on the other side. AUC, what does that stand for? If you look at your table or wheel, that stands for ILE. Finish up the next 3 and then come back and see if you're right. GCC codes for arginine, ARG. UAC codes for tyrosine, TYR. And then UGA codes for stop. And yes, actually write the word stop when you're doing these for me, because I know that you didn't skip it then. This is what stops the process. So here we have our beads on the necklace. Each amino acid gets stuck together with a peptide bond. And then you have your protein, which can go off and be modified and do its job. Your protein is just about done, like I just mentioned. Most likely gets modified. Here's some examples at the bottom. We can tack different things on, sugars, phosphates, etc. And then it can go off and do whatever its job is. Those are the basics of translation. Check in your note back at what's next and see me if you have any questions.